Okay, we're now going to wrap things up by doing a kind of a sketchy proof of the Bode sensitivity integral. So let's just start by reminding ourselves of what everything is. So the Bode sensitivity integral tells us that the integral with respect to frequency of the log of the size of the sensitivity function is equal to a constant. And that constant depends on the number of right half plane poles of the return ratio L, so the product of everything in the feedback loop. And what it tells us is that basically it tells us given a plant with a certain number of unstable poles, whatever we do with our controller, this conservation law will be satisfied. And this has a big impact because, as we also saw, much of feedback could be understood in terms of trade-offs involving the sensitivity function. So in order to get good disturbance attenuation, we wanted to make the sensitivity function small. In order to make the input-output behavior of our closed-loop system not very sensitive to changes in the process model, we needed the sensitivity function to be small. And the Bode sensitivity integral says, fine, you can make the sensitivity function small in some frequency range, but you're going to make it bigger in some other frequency range. And in that frequency range, the opposite of what I just said would be true. If the sensitivity function is big, then you don't have good, your input-output closed-loop behavior won't be invariant to errors in between the real plant and your model of the plant. You won't get good disturbance attenuation. And feedback is then just about managing this trade-off. You choose the frequency ranges where you think it's most important to have good performance, good disturbance attenuation, this kind of thing. So that's the sensitivity integral. Let's just have a stab at deriving it. And just for simplicity, we're going to derive the case where the conserved quantity is equal to 0. And this corresponds to the case where you have no right half plane poles. Things are always worse if you have right half plane poles, including the proof. But hopefully we'll I'll give you some clues as to how you would extend this at the end, if you wanted to take into account the right half plane poles. So our basic strategy is going to be to turn this into a contour integral. And really, I just want to give you a flavor for the proof strategy. So we're going to turn it into a contour integral, and then we're going to use this residue theorem to and match up various bits of the contour integral to deduce this sensitivity integral here. So the first thing we're going to do is we're going to just do some manipulations. So the first thing, we're going to make this go from minus infinity to infinity. For negative frequencies, this just becomes complex conjugate, and the absolute value of the complex conjugate is the same. So the effect of doubling the range of integration just means we have to halve the overall thing to get back what we started. And we're also going to simplify this 1 over L thing. So we can write that as log of 1 minus log of 1 plus L. Log of 1 is 0. So we could have a minus sign there, but I'm going to immediately get rid of that minus sign, and I'm going to put a J in here. And maybe you just want to check at the end that I've not sold you a lie. Actually, all of this stuff in the front is not going to matter, so we can afford to be a bit sloppy. So what have we done? We've introduced two J's. They multiply to give -1, but we've also got a -1 because we've just got rid of this 1 over 1 plus L. Instead, fine, and then we doubled the range and halved the overall thing. So nothing too big so far. Why did we do this? Well, that will be revealed in just 1 second. But first of all, let's deal with some other things. So another annoying thing here is we've got this absolute value. But we've seen before that logs of absolute values of things just correspond to real parts of the log function. So rather than looking at the log of the absolute value, let's look at the real part of the log of the unabsolute valued thing. And then, so we could pull the real part through to here, but let's actually pull it all the way through to here. And so pulling it through the j, it just becomes the imaginary part. And we'll keep the half out here. It actually doesn't matter, as we'll soon see. Does matter if you want to do all the bookkeeping for this, though. But I'm not going to do that because I'll probably make a mistake. So nothing's changed so far, but now we don't have the absolute value anymore. And then we've got our j d omega in here. So why did we introduce this j? And this is really just to set things up as a contour integral. So let's just try and remind ourselves very briefly how we do contour integrals. So the way we write it is we say we integrate over some contour, typically denoted by gamma. What do we integrate? We integrate our function with respect to s. And what this means is that we integrate f of s as s moves along this contour. Of course, if we want to actually evaluate this integral, what we need to do is come up with a parameterized description of our contour. And the way you typically do that is through this intermediate parameter t. And now we run over some limits so these are now real numbers. A corresponds to the value of t that starts our contour, b corresponds to the value that ends our contour, and then we have f of s evaluated at these values of t, and then we have ds dt dt. So the idea is that s of t, as I put in values of t between a and b, s of t traces out the contour that I'm interested in. So now this becomes clearer when you actually try and do a particular example. So let's now just focus in on this and try to turn this into a contour integral. So let's say we're trying to integrate over our friend. So this is the complex plane, and our friend is the old Nyquist contour. And the Nyquist contour, if you remember, it was this big semicircular contour that went something like this. So let's start off just by trying to integrate along this bit of the Nyquist contour. How could we turn this into some contour integral like this? Or how can we parameterize this part of the contour? Well, it's so obvious that you may not even, you may miss it, I guess. So how could we parameterize that line? Well, we could just say s of t is equal to j times t. And then we put in the value of t is equal to minus r here, and we run all the way up to plus r. And taking limits will just be a bit sloppy here. So if I wanted to, well, let's not be sloppy just yet. So we're going to say that this semicircle's at some radius r. And so if I want to do a contour integral along this, I would integrate from minus r to r of whatever I'm trying to integrate, and then s of t is just j of t, ds dt is just j, and then dt. So that's how I would integrate along this contour here, and taking the limit r goes to infinity, we get the whole of the imaginary axis. And that's what this, I mean, whenever you have a minus infinity and plus infinity, you're implicitly saying take the limit. So actually, this thing here is exactly this thing here, just with f of s equal to log of 1 plus L of s. So what we managed to do is if we call this part of our contour integral I1, that's exactly what this is referring to. And so now we've got some sort of a strategy for going about our integral, because we also know this theorem from complex analysis, that if we integrate an analytic function, or a function that's analytic on some domain, on a closed contour, typically you would do anti-clockwise. For the analytic function case, it doesn't matter because we get 0. But if we integrate along some contour where the function is analytic both on the contour and on the interior, then we get 0. So if I say this integral here is I1, this integral here is I2, well, as long as my function is analytic in this region here, then by the residue theorem, I get that I1 plus I2 is equal to 0. And this is what we're going to use, because I1, this integral, this is the thing that we're interested in. We're now going to do the integral I2, and we'll find that our function is analytic. And so what we'll have is that I1 is equal to minus I2, and then, well, surprise, surprise, I2 is going to be 0. Okay, so that's our plan. So, first of all, how can we determine that our function is analytic? Well, we've actually sort of seen this in the past for the log function, and the key observation here is that if L has no right half-plane poles, then 1 plus L has no right half-plane poles. And similarly, if the closed-loop system is stable, then 1 plus L can have no right half-plane zeros, because the poles of 1 over 1 plus L are the zeros of 1 plus L. So under this assumption of no open-loop right half-plane poles, provided the closed-loop system is stable, which is necessary to have a bounded sensitivity function. If you're unstable, the sensitivity function is just infinite. Well, yeah. Anyway, we want the closed-loop system to be stable. Then this thing here has got no right half-plane poles or zeros, and actually that means that the log, this function will be analytic in our region here. So we've established this. All that remains is to find the integral I2. So, and this is where our assumption about the relative degrees in the numerator and the denominator come in. So you remember when we introduced the Bode sensitivity integral, we said in order for this to be true, the numerator powers of L had to be 2 less than the denominator powers of L. And another useful way to write this for our purposes is that 1 plus L is going to be approximately equal to 1 plus A over S to the n for large S. So because the denominator has got higher order than the numerator, when we make S very, very large, those higher powers tend to dominate everything. And so we'll get something that will asymptotically behave like this. And we know from this relative degree thing that n is greater than or equal to 2. So the denominator has powers of S that are at least 2 larger than in the numerator. So when we take this approximation for large S, then we'll have something that goes like A over S to the n. And why is this useful? So this then implies that log of 1 plus L is approximately equal to. So as S gets large, this quantity here gets very, very small. And I don't know if you remember, but log 1 plus x for small x is approximately x. So for large values of S, log of 1 plus L is approximately A over S to the n. And this is what we're going to use to finish off our integral. We're going to integrate this along our contour I2, and then taking the limit r goes to 0, this approximation is going to become exact, and we're actually going to find that this thing goes to 0. And you can make everything rigorous if you are so inclined. So all that remains is to work out how to do this integral here. So to do that, we just need to come up with some suitable function s of t that's going to trace out this part of the contour. And, well, a good choice is r e to the minus j t. And then how should we get these sets of points along this contour? Well, we should just start t at minus pi over 2. So minus pi over 2 means we'll start here. And then if we increase t to pi over 2, we'll go all the way round to here. So this is our contour. And so when we go through all of these steps here, we find that we want to do the integral from minus pi over 2 to pi over 2, whatever our function is, evaluated at r e to the minus jt. And now ds dt is just minus j. Minus j r e to the minus jt. So that's ds by dt. And then we integrate this with respect to t. So now we just want to actually integrate our log function, which we're going to say is basically like integrating this. So substituting in, we'll substitute in. We now know we want to integrate from minus pi over 2 to pi over 2. And our function is a, and then s is equal to, so we've got an r to the n, and then an e to the minus j n t, and then here I've got minus j r e to the minus j t dt. And if I just go and simplify this, I get the integral, same limits. I have, well, minus j a, and then here I have r to the 1 minus n, and similarly I guess e to the minus j t 1 minus n dt. And we can evaluate this integral if we want. We don't, and maybe you should, just to check things for yourself. But the key thing here is because n is 2 or more, then we've got an r to the minus 1 at least. And that means as we take the limit, r goes to infinity, this term here is going to collapse to 0, and we're going to get this integral here is all equal to 0. And that's going to finish everything off. That means that I2 is equal to 0. If I2 is equal to 0, that means I1 is equal to 0. If I1 is equal to 0, then following all the way back here, we get that the Bode sensitivity integral is equal to 0, which was what we wanted to show. So finally, just some clues for how to extend this, if you want to have a go yourself. I think the easiest way is if L has some right half plane poles, then so you should look at 1 plus L, and then you should multiply this whole thing by s minus p over s plus p. And you need one term for every unstable pole. And then, just by, so you multiply the whole thing by 2 terms like this, 1 for each pole. So this is just equal to 1. And then you use the log to split this. So if I'm looking at the log of this now, and I just split it with the multiplication property, then I get log of 1 plus L, then I've got an s minus p, s plus p, plus log s plus p over s minus p. And now the critical thing is that this term here, this is now just going to cancel the unstable pole. So this function will be analytic, and so maybe we have more unstable poles in here, but whatever ends up here is just a type of function that we've already dealt with So we know that this term from the integral is going to contribute 0. And now we just need to, so we've collapsed the whole thing down to integrating this function here. And if you go through all the steps, you'll have one of these for every one of your unstable poles, p. And you'll end up, if you do things correctly, being able to show that this thing here is equal to the sum of the right half plane poles multiplied by pi. And you just need to be a bit careful doing these integrals here. There you go. I hope you kind of get the general strategy for the proof at the very least. It's just we're just doing it because there's no real reason more than that. But the Bode sensitivity integral itself is very important to remember when doing your control system design. So